Okay, everyone, here's part 3. So here's where we left off talking about the thermohaline circulation and what impacts are seen in that from climate change. And now we're going to switch or kind of continue that, but looking at it graphically. So our changes in deep water circulation, remember we talked about the North Atlantic being especially sensitive because of where the North Atlantic deep water drops off and sets up that momentum for the conveyor belt. So we have a couple of different things that are happening here. First, we have warmer surface waters, and then we have a lot of melt that is being deposited into the ocean at this space. So that's coming from glaciers, which are concentrated up in this area, and then also from your polar ice caps that are not freezing or staying frozen. So a lot of that fresh water is coming back into the system. So remember that warmth and salt content are the two main factors that impact that conveyor belt. So if we're warming the water, we're making it less dense. And if we're adding fresh water to it, we're making it less saline, which is also making it less dense. So we're kind of getting double whammied up here by lessening both factors. And so as a result, we run the risk of not having our roller coaster have as big of a takeoff into the conveyor belt. And so that analogy really holds true because we talked about how if the first hill on a roller coaster isn't high enough, the roller coaster doesn't have enough energy to complete its course. So what that means is if we don't have enough energy and if we don't have enough momentum provided by this drop off in the North Atlantic deep water, then our conveyor belt could be impacted in how it circulates around the whole world. That's going to impact the heat transfer and the balancing of the heat energy throughout our global environment. So what we see with this polar ice melting is what's called Arctic amplification. We have lost more than 2 million square miles, or 2 million square kilometers of Arctic sea ice in the last decade. That loss of ice has meant enhanced warming due to, and this has been a long time since we've talked about this, but due to lowering of the albedo. And remember that albedo is reflectivity. And so remember that if sun gets reflected off, it keeps temperatures lower because it's not being absorbed. Well, if we lose that reflectivity, then more energy is absorbed instead of being reflected off, increasing the warming that we experience. So if we look at that visually speaking, this is a composite of satellite data. Our North Pole Arctic sea ice is as of 2012 was this small compared to the 30-year average of this yellow line. So that's all that fresh water that's being released back into the ecosystem in that area. So remember that creatures are either stenohaline and euryhaline as well as stenothermal and eurythermal. So this is going to impact those creatures in both of those ways because not only are we warming in this area, we're also changing the salinity of the water by adding that fresh water in. So again, we look at overall trends, not individuals' peaks and valleys. So our climate experience natural variations, and some years are different than others. But what you see beyond those natural variations year to year in sea ice is that we have this overall declining trend that matches our overall increase in temperature that we're seeing. Now, the impact that this is having starts at the top of your food webs. So polar bears have to be able to stand on the ice in order to have a surface to go fish from. Well, if they can't stand on the ice because there isn't any, we have polar bear drownings that are happening. And then also they're starving because your food sources are dwindling and they're migrating to other locations. Remember that if they are not able to handle that temperature variation, they have to go elsewhere that is in their sweet spot of temperature. So we have their food sources that are migrating elsewhere to find their ideal temperature range. We have Antarctica that is shrinking. The continent is obviously still there, but their ice shelf is shrinking. And their glaciers are still there. We're not to the point where they're receding, but they're thinning. So we can measure the thickness, the relative thickness of glaciers using satellite data and then manual measurements as well in places. And we can notice that they are thinning. So one of those is called the Larsen Ice Shelf. And over the last decade, it's decreased more than 40% and has not rebounded in the winter seasons, which is concerning. We have, since 2006, lost 200 billion metric tons of sea ice. So that's 200 billion metric tons of fresh water that have been added back to those ecosystems. And interestingly enough, West Antarctica is one of the fastest warming places on Earth. So this has to do, this kind of falls in line with what we were talking about, that polar amplification. For whatever reason, West Antarctica is experiencing high rates of change. So again, it's not now the warmest place on Earth, but the rate at which it's changing is very high compared to other places. The next thing we need to talk about is ocean acidification, and this is something that is likely affecting your creature, whether that fishery has realized it or not, whether that population has realized it or not. When we have atmospheric carbon dioxide dissolved into the ocean water, we see with that abundance is, oh my goodness, we see that abundance cause a pH difference in the water. So seawater is slightly basic. It's about 8. I'm gonna have to wait. It's about 8. And what we see, 7 is neutral. So anything that moves in the acidic direction, so it doesn't actually have to become acidic, but if it moves in the acidic direction, it already starts causing issues. So we have had a 30% increase in hydrogen ion concentration. So for those of you who have explored acids and bases, you know that that's the measure of acid content. And we see this acidification affecting things with shells. So coccolithophores, forams, sea urchins, corals, things that have hard pieces that are affected by that acidification. So if you look at these creatures, these are the ones that we're talking about. Okay, coccoliths are phytoplankton. Pteropods are like little baby snails. They're a type of zooplankton. Sea urchins, corals. These are the ones that are most affected by ocean acidification. So look at a pteropod. So this is a normal pteropod shell, but after 6 weeks of being exposed to ocean water that is more acidic than it should be, you can see the breakdown of the shell. Well, if the shell goes away, the creature goes away, and there goes a very important bottom part of your food web. So what we see is that as carbon dioxide dissolves into the ocean water, it has to absorb it some way, and it does that by converting it and reacting with it into different areas. And that causes the pH to decrease. So we're not going to get into the whole chemical composition, but just know that by dissolving carbon dioxide in the ocean water, it creates different chemical compounds than what are in abundance right now that are causing the decrease of the pH. Rising sea level, we have already mentioned. It's already occurring. The main cause of sea level rise is not what you would think. The main cause of sea level rise is not melting. Although that is one source, the main cause of sea level rise is thermal expansion. Our deep ocean waters are warming faster than any other of the ocean, even than the surface waters. And the problem with that is that that's a ton of water. If it expands, it bubbles everything up. It balloons everything up. If you've ever done the experiment by putting a balloon in a freezer versus looking at it in at room temperature, it shrinks when you put it in the freezer because the air condenses. Well, air and water are both fluids, so that property is of water as well. So as water warms up even just a little bit, it expands, and that's what we're seeing with this thermal expansion. So the main cause of sea level rise is thermal expansion. It's due to warming, not melting. Now, that doesn't mean that melting fresh water coming into the ocean is helping any, and certainly having local effects in the areas where it's most abundant. So we have these average sea levels. Again, we can look at the overall trend versus our, yearly variations, and we can see that it's different at different latitudes. So in the northern latitudes and southern high latitudes, northern and southern high latitudes, we're seeing greater sea level rise, and then at our mid latitudes and our equatorial latitudes. Part of that has to do with how much warming is taking place in that deep water. So there's so much deep water in those areas, even little changes are big ones. This is, again, one of those overall trend lines looking at sea level. And this specifically is measured from an Argo float, which we talked about way back in the beginning. And again, we look at 60-day averages. There's all these peaks and valleys, but we look at that overall trend to look and see what's happening. And this is change in mean sea level, so average sea level. Severely affected areas are those with gently sloping coastlines. So the US Atlantic and Gulf coasts are highly impacted by that. If we continue at our current rate, we're going to see anywhere between a half and 1.5 meter. So that's between a 1.6 and 4.6 foot increase by the year 2100. Other predicted changes that we're seeing start or see kind of the pieces falling into place for that to happen. Sound transmission in the ocean is impacted by temperature. And so those creatures that rely on sonar to find their food and communicate can be heavily impacted by that. We have reduced dissolved oxygens in our marine dead zones, which we've talked about at length. And then we have increased wind speeds and wave heights. So remember that weather is a balancing act. So if you have your differences between low and high pressure get bigger, then wind has to move faster to balance that. Wind drives the waves, and so our waves become more intense. We see migration of mangroves. Mangroves in Florida are actually migrating north, which is very interesting to watch happen. And that's something that has been more of a recent discovery. Our ocean productivity changes. So our increased stratification of the ocean, so we have our really strong thermocline that's happening in places that normally wouldn't have a strong thermocline, cuts off the mixing of layers, and so it cuts off your upwelling in a lot of places. So therefore, when you get your phytoplankton, you're supposed to get your phytoplankton from upwelling, and it's not happening, that creates a problem. On marine organisms, we've talked at large about sensitivity to water temperature and salinity changes. So obviously, you need to know whether your creature is eurythermal or stenothermal, eurysaline or stenosaline. Haline, excuse me, that's not right. Euryhaline or stenohaline, and you need to know what that's going to do to your creature. You have migration and changes to populations of those fish groups, and those migrations are going to happen into deeper waters where they're less accessible and toward the poles where they're less accessible. Remember back to fisheries, if those fish are now outside of the boundaries of your fishery, that's just tough. The government sets those boundaries, so you have to fish within them. If those fish aren't there, then you lose your livelihood. And again, here's that image where you see the polar intensification. So surface temperatures have risen mostly since 1970, and the deep water is showing those increases. And that is it for climate change as it relates to marine organisms, and also wraps up our kind of series on issues that are facing marine organisms. So remember that you're going to be kind of picking out all of the pieces that relate to your creature and tying that into your project and your presentation that you're going to be giving. Presentations are due Friday, and then we will actually be delivering our presentations in small groups next week, and we'll get that set up. I hope you guys have a great day. Bye.